So once again, may I ask, is there any questions? Nope, nope. Okay, let me re-explain Hess's law because students have a really hard time with this typically. And it's one of those things, and I guess I'm the weird one. I like Hess's law because it's a puzzle. I just like puzzles, you know? And the students tend to not like this as much. But if you look at the rules of enthalpy delta H, so if you multiply an equation by some factor, the heat of reaction is multiplied by the same factor. Makes sense? So if you get 100 calories from eating one candy bar, if you eat two, you get 200. And if you eat half of one, you get 50, right? Makes sense. Then if the chemical equation is reversed, delta H reaction changes sign. So, which means that the energy that I get from eating a chocolate bar and then teaching class, that's the same amount of energy that is needed for the plants to photosynthesize and make the sugars that went into the candy bar, right? And then if the chemical equation can be expressed by a series of steps, the heat of reaction for the overall equation is the sum of the heats of each step, which also makes sense. So for the candy bar, the energy that it takes to make the glucose, the energy it takes to make the sucrose, the fructose, and then to join together to make the sucrose and that kind of stuff, all the steps summed together, each energy step is equal to the overall reaction, which makes sense. And this is an image kind of showing Hess's law here. If this going from here to here is the overall reaction shown there, and if there's an intermediate step, if you look at this arrow, so that arrow plus that arrow equals the arrow here. So that's just showing the different potential energies, and you sum them up, and then you have the overall potential energy change. So, questions so far? So let's apply it then to Hess's law. And so here's a chemical reaction that is going to be extremely hard to figure out. So, or at least or to actually do in the lab. Take carbon and hydrogen and mix it together to make propane. I mean, there's a lot of different products can happen when you do this. Propane is one of them, but it's probably a bunch of other things. But trying to control this experiment is going to be really, really difficult. But you know what's not difficult is burning stuff. So it's a lot more fun too, right? So you can burn propane, burn carbon, and burn hydrogen. So, but because of Hess's law from these equations here, you can write them and you can figure out that relationship there. And what I always do to start off with, I just write the first equation is H1, the second one is H2, the third one is H3. And now I look to see where the reactants and products are. So C3H8 propane is on the product side. So I have to flip this equation. 3CO2, I know the states, plus 4 waters yields propane plus 5 oxygens. And we flipped it, so it's minus H1. And then carbon is on the left side, so this is fine. Carbon plus oxygen makes carbon dioxide, and same thing with hydrogen. So this is H2, H3. Okay, so there's two ways you can approach this, and this is actually I'll do it the other way because I can erase it. One of the ways you can look at this is to get rid of the oxygens here. So actually, this one you guys have to do by trial and error. Oh no, I guess the water. So you can look to get rid of the one of the strategies is to get rid of the intermediates. So water and oxygen are the intermediates. So how do we get rid of these? Water is only on the bottom equation. So you can multiply the bottom equation by 2. And if you do that, you get 4, 2, 4, 2. So now that these 4 waters, when you add them together, will cancel. Now you have to look at the oxygens. You have 5 oxygens here, and you have 2 oxygens here. You need another 3 oxygens. So you can have the 3 oxygens by multiplying this equation by 3. And you would get 3 such as that. And then 3 plus 2 is 5. So those can go together. And then these oxygens will cancel. And I already mentioned the waters will cancel. Then if you add this together, if you add these 2 equations together, you get, oh, I'm missing the CO2s. Oh, and the CO2s also cancel. You get 3C plus 4 hydrogens make C3H8. And that's minus H1 plus 3H2 plus 2H3. So that's one way to do it. I don't like that way. The way I prefer to do it. Does anybody have any questions with that way? I know it bugs. Hopefully it's not bugging you guys. Sometimes people don't like it when I show multiple ways to do problems. But the way I like to do it is to look at the reactants. So 3 carbons, 1 carbon. So I multiply this by 3. And 4 hydrogens. This should be 2, 2. 4 hydrogens, and there's 2 hydrogens here. So I have to multiply the bottom equation by 2.
Equaling it out, like, so that once you get rid of all the reactants and products, you're just left with the top equation.
Yes, exactly. If you notice, because this and that are the same thing. And so now the same thing is when you add them together, when you add these 2 equations together, the waters cancel, the CO2s cancel, and then the 3 plus 2, 5, and then the oxygens cancel, and we're left with that as is. And
the change in heat, you have to do the same to that because it's part of it.
yeah, it's part of the equation, right? So it's, if instead of carbon, it's candy bars. If you eat 3 candy bars, you get 300 calories instead of just 100. Right, and if this is a peanut butter cup, if you eat 2 of them, you get twice as many calories.
And it's important for the top one because you put the propanes on the left side when you need to be a product.
Yeah, the first equation, propane, is on the reactant side. It needs to be on the product side. So you flip it.
Yeah.
Other questions? And so it's going to be minus H1 plus 3H2 plus 2H3. So it's going to be minus a minus 2043 plus 3 minus 393.5 plus 2 minus 483.6. And that equals to negative 105 kilojoules per mole reaction. So
and when it's negative, does that mean that it's giving off?
Yes, it's exothermic. Heat is leaving the system.
And going into, when it turns into propane, it's giving off heat?
Yeah, this overall relationship is going to be exothermic.
Okay.
But do you notice that's negative 105 versus negative 2000 for the combustion? So it's
Gotcha.
not nearly as exothermic as the combustion reactions.
Makes sense.
So, other questions? All right, your turn. And I do encourage you to play along because most students have a really hard time with this. You're trying to solve for this one. Oop. You want to know this. And you're given does anyone just have no idea how to do this?
So the first one, do we flip that? Put 2NO on the other side?
Yeah, and not only that, NO2 is on the wrong side as well. I'll go ahead and write that. How you doing, Zoomers? You doing all right? Tricky. You underestimate the sneakiness. Am I so old that you guys have never seen Mr. Deeds? My 21-year-old nephew, whenever he talks, I have no idea what the hell he's saying. Yeah, I still just get the negative sign. I haven't gotten the positive yet. Yeah, the NO2s and N2Os, and that's another.
Too many 2NO.
Guess I should open the chat. That's one thing I didn't do. So do you think A?
2 more seconds.
Oh, okay.
Yeah, 2 more seconds.
Okay. Take your time. I like doing nothing during class time. It makes my job exceedingly easy. Yes, I'd rather instruct well. Oh, speaking of which, I think we're gonna have extra time. Did you guys not like the problem session last time? I was thinking about what else I could spend class time on. I was thinking about doing some study skills. Would that interest you guys more than problem session? Yeah. Okay, all right.
Wait, what's the difference? So it skills and problem.
I would talk about how to like take tests and strategies how to take tests and yeah. Yeah, we can talk about that.
Instead of more of these.
Yeah.
These are the tests.
Yeah, these are.
Whatever, the majority.
Somerset. I got invited.
So, well, I guess I'll spare everyone. Some people think A, I think B, C, okay, D. Yeah, the answer is C. The zoo. You although some of you didn't answer C. Or did you get stuck somewhere?
Well, I was looking at the second, or really it's the third equation down, and I know that we have to like equalize it, but I wasn't sure if I had to multiply the top equation, the one given, by 2, and the bottom, and the one in the middle by 3, so that way they're equal to each other. And I see that you did multiply it by 2, and that's what I was thinking, but
Yeah, because if you multiply this one by 2, you get 2, 2, 4. Okay, and when you do this, then when you add them together, those cancel, and these is 202. So the 202s cancel, and then you get, when you add the equations together, you get 2 NO2s plus 2 N2Os makes 6 NOs, and your original one is half that. So you have to divide this by 2. So that means you have the opposite of H1 plus 2H2 plus just H3. So it's going to be minus a minus 113.1 plus 2 times 182.6 plus a minus 163.2. All quantity divided by 2, and that should be 157. Like that.
I forgot the canceling out within the 3 equations.
Yeah. Well, then don't forget it on the test. No, by all means. It is much better to have your confusion and mistakes happen inside the class than, yes, or even worse when you're taking the assessment. You got it? All right.
I tried to multiply by 2. I think it's better.
Yeah. Yes. You could multiply by 2, then divide by 4. That's another option you could do. Is that your, I'm raising your hand? Oh, it's a fly swatter. Yeah, I didn't realize these COVID tests were so versatile.
It's so fun.
Yeah, it's now a mini fly swatter. All right, now everyone's playing with it. This is what you're missing, Zoomers, by not coming to class, is playing with your COVID tests. And And now someone is licking it like a lollipop. Or is it sucker? Which one do you guys use in this? It's a lollipop or sucker? What was the? I know that different words for different regions in the country. All right. Any questions? Anyone? No? All right. Good. I'm glad you got that. Students have a hard time with that. And now on to the last topic, standard states. So I'm sure everyone has done this before. Why should I do the homework assignments when I can copy my homework assignment from the smart student in class, right? So that's what we can do that kind of sort of in thermo by using something called standard states. Because remember that that the enthalpy H and E internal energy, it's path independent. So if we don't even have to do experiments. If someone else has done things, we can just figure it out from the previous stuff and don't even have to do the experiment. Because we're probably realizing, I mean, look how hard it was for us just to put 6 drops into a COVID card and slide in a whatever you call this, the nose applicator, and turn it 3 times and close it. That was just, and that's an easy experiment, right? All these other experiments, there's so many more things can go wrong. So why do experiments when we have thermo? So we can take standard states, and I'll show you how we can apply it in a chemical reaction. So standard states, and this is what we do in the United States. I think in Europe too. Russia is slightly different. We found out, although I think Russia has adopted our standard states, although I think their temperature is a little different. If it's like 20 or 23 degrees Celsius. Ours is 25, probably because Russia is so cold. So the other thing is Russia uses 100,000 pascals as the standard pressure. We use 1 atmosphere as our standard pressure. And that, I think Russia makes more sense.
They're still better at chess than us.
I don't know, man. I saw the Queen's Gambit. Although that was a fictional story.
It was actually based off Bobby Fischer.
Yeah. But they're good at chess in Hungary too. I used to live in Hungary. But so I know about this because we collaborate with the Russians now on the International Space Station. So we do a lot more collaborative stuff with the former Soviet Union now. But for a long time during the Cold War, we just developed things separately. And for us, our standard states for gas, it's the pure gas at a pressure of 1 atmosphere. For liquid or solid, it's the standard state is the pure substance in the most stable form at 1 atmosphere pressure and a temperature of interest, usually 25 degrees Celsius. And a solution is the concentration of 1 molar. So what I mean by liquid or solid, and actually also for a gas. So look at carbon, for instance. Carbon can be C60, C70, graphite, diamond, or nanotubes. We pick graphite. So graphite is usually you pick the easiest one or the most stable, and in fact, the most stable for carbon at this temperature and pressure is graphite. So also for gases, I mean, if you look at oxygen can be oxygen radical, just single O. It can be O2, diatomic oxygen, or it can be ozone, O3. We pick diatomic oxygen. So it's usually also the more common one as well. So that's why we pick oxygen as a standard state. And the enthalpy change, standard enthalpy change, and when we have the standard states, we put this little degree sign, on it. So the change in enthalpy for a process when all reactions products are in their standard state. So, and then we have the enthalpy of formation. That's when you have 1 mole of compound made from their elements all in their standard states. And we also define enthalpy of a pure element of the heat of formation to be 0. So heat of formation, actually the previous lecture, well, not lecture, it's still the same lecture today. This would be the heat of formation of propane. So because here, if you look at this one, you're making 1 mole of propane from the elements carbon and hydrogen. So this would be the heat of formation of propane. So, and that's when we do the heat of formation. And notice that and enthalpy H is actually a relative measurement. So there are some things that are absolute. Temperature is absolute because 0 temperature means things are not moving. Okay, so that enthalpy H is always relative to something. And we pick the relative points to be elements. Yeah.
I think so for temperature, if it's 0, they can still spin.
It's temperature is defined as translational kinetic energy.
Okay.
Spinning is rotational kinetic energy.
Okay.
It's like saying I have no money, but I have 100,000 shares of Microsoft stock. It's true that I have no money, but I have assets, right? So something with 0 Kelvin is not moving translationally, but can still be spinning or vibrating.
And then could turn into transition.
At absolute 0, it would not, because it has to work. Well, it would have to have a collision. So it doesn't matter, any kind of collision would take it out of absolute 0 anyways. So yeah, but the transition happens from rotational and vibrational to translational via molecular collision.
Only collision.
Yeah. Yeah. I guess you could have a decomposition reaction where one thing, if it was spinning and it decomposed and flew off, then it could go.
Mhm.
But that would be a rare case.
I was thinking like quantum computing and they super freeze like the contents and then.
Yeah, I see your point. That they have done experiments on that, and they have shown that crystals at 0 Kelvin or near Kelvin do have uncertainty in their position.
Yeah.
So, but that's the uncertainty position is not necessarily motion. So, because in order to find the uncertainty, for something to be uncertain, you have to actually probe it, and then by probing it, you lose the 0 Kelvin anyways.
Yeah.
Yeah. So, very advanced topic. Okay. Don't worry, that's not on the test. So, other questions? So yeah, enthalpy, we relate it all to the elements. And see here are some standard heats of formation or enthalpy of formation. Usually just use heat of formation. And so for instance here, bromine, you can see bromine is an element, it's a liquid. It's the element, the heat of formation is 0. And then HBr, of course, this would be H2 would be 1/2 H2 plus 1/2. Well, it's going to be gas plus 1/2 Br2 liquid, making HBr gas. And same thing that we did with like the propane example. You would then usually we do combustion because those are just easy experiments to do. You can do that. And if you did the Hess's law with that, you would find out that that would be minus 36.3 kilojoules per mole.
If it's 0, does that mean that's its natural state?
It's either very weird that it's 0 or it's the element. I can't think of any, off the top of my head, I can't think of any reaction that would be 0 other than the element itself. So you see here all of them. So oxygen, if you look at oxygen, O2 is 0. Silver metal, 0. Sodium metal, 0. All the elements, carbon, graphite, 0. And diamond, carbon diamond is actually higher in energy. So of course the opposite is true. If you take a diamond out in this temperature and pressure, it will slowly revert back to graphite. Just like graphite Graphite over time turns into diamond. The opposite is true. Diamonds turn into graphite.
So if you bought a diamond over time, it would go back to graphite?
Yeah.
How long? Like thousands of years?
Probably millions. A long time.
So we don't need to worry about it.
Not really. Not really. The De Beers commercials are wrong. Diamonds are not forever, but they do last a very long time. Other questions? Okay. So because things are path independent, you can do this. The standard, so remember the zero is standard. The standard heat of reaction equals the sum of the number of moles. So this is the number of moles of products times the heat of formation of the products minus, oh, and this capital sigma, it means sum. The sum of the moles of reactants times the heat of formation of reactants. Did you guys know that this, geez, I can't write sigma, that this equals sum? Are you familiar with that? Okay. So this is known, the sigma series is an arithmetic series. So if you have the sum of n equals 1 to 3 of 1 over n, this equals 1 over 1 plus 1 over 2 plus 1 over 3. So that's what that operation means, the capital sigma. Then you have a geometric series, capital pi is the product, or geometric. So if you have pi of n equals 1 to 3 of 1 over n, this is equal to 1 over 1 times 1 over 2 times 1 over 3. So let's see if I can do the math in my head. This is going to be 1 and 5/6, right? So it's going to be 3/6, yeah. And this is going to be 1/6. Right, so if you do those two operations, this is a math operation, but sigma means sum. And always let me know if you ever see a math symbol or something like that. And that's the other thing that's weird about chemistry. And also you guys are taking this class for the first time you're seeing some of this stuff. Chemistry borrows notation from math, physics. We have our own notation, and we actually sometimes use different notation than physics. We got to thank the Germans for that.
Like heat?
No more frequency and wavelengths. We'll talk about that later. And for some reason, we call magnetism H instead of B. So, all right. So let me do the sum here. Use the standard of enthalpies of formation, determine the standard heater of this reaction. So using this equation here, so the delta H0 reaction is going to be equal to the sum of heat of formations of products. So it's going to be 4 delta H0F of NO. I should even specify gas, plus 6 delta H0F H2O gas, because liquid is different than vapor, minus the quantity 4 delta H0F NH3 gas, plus 5 delta H0F of oxygen gas. Right, okay, there we go. Sorry, that one's a little ugly at the end.
Just 10 minus 9.
What?
10 minus 9?
No, 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 no. You have to look these up.
Okay.
Okay. So you get the 4 from here. Oh, no, a second.
No.
No, no.
Yeah.
Yeah. 4 from there. I just saw 4. 6 from there. That 4 from there. We'll do green. Hopefully, if you're colorblind, I'm just using different colors to show where they're at. So, and you can see that so the products are this side of the equation, the right side of the equation, so they come first. 4 times the heat of formation of NO plus 6 times the heat of formation of water minus 4 times the heat of formation of ammonia plus 5, and that quantity within 5 times the heat of formation of oxygen. So let me get rid of all these green lines. Oh, but I wanted that one. Okay. So now the next step, you have to look it up from the chart. So you go to your handy dandy chart. So 4 of NO. So where is nitrogen? NO gas is right here, 91.3. So 4 times 91.3 plus 6 times water. Okay, and make sure that you use the gas because the liquid is a different number. So minus 241.8. 0.8 minus the quantity 4 times nitrogen monoxide. Nitrogen monoxide. Oh, no, I'm sorry. The ammonia. What am I doing? 4 times ammonia minus 54.9. I'm probably 45. 40 minus 45.9. I did that right? Yeah, minus 45.9. And then plus 5, and oxygen is going to be 0. Because oxygen is an element, so that one's 0. So now you just plug this in. And where is this? Okay, here we go. And doing this, you get minus 902.0 kilojoules. So per mole reaction. Okay. So recap with this one. We have this equation here. 4 ammonias plus 5 oxygens makes 4 nitrogen monoxides and 6 water vapors. And we want to know what the standard heat of reaction for this is. So what we do is we look at the smart people before us, and we use the top equation here. The heat of reaction is the sum of the moles of products, heats of formation of products, minus the sum of the moles of reactants, heat of formation of the reactants. Then we apply that. So we have on the product side, 4 moles of nitrogen monoxide plus 6 moles of water here, minus the reactants, 4 moles of ammonia and 5 moles of diatomic elemental oxygen. We look those numbers up and then we solve for it and we get minus 902 kilojoules per mole reaction. So questions on how to do that? Okay. Students tend to love thermo because, oops, I gave you the answer. Ignore that. This is also known as a thermite reaction. So actually, I can show you the thermite reaction. Where is elements in action? This is going to be iron. No, it's going to be, is it aluminum or iron? Is it iron? Oh yeah, here we go. Here's the thermite reaction. So that's aluminum powder and rust. You throw the mixture, and then you have activation energy, something usually magnesium, like in a sparkler, is used. And then when it hits it, it does the thermite reaction. And it forms iron. Yeah, that's iron. It's very, very hot, very exothermic. So, and although the thermite reaction specifically makes liquid iron, but I put solid iron because the heat of formation of solid iron is 0. This is an element. So what is the standard enthalpy of reaction for this one here? Has anyone ever heard of the Hindenburg before?
Oh, the humanity.
So the Hindenburg was a Zeppelin. So it was a floating aircraft that used hydrogen. So we have blimps that use helium. So it was a hydrogen-filled Zeppelin, and it had paint on it that had aluminum in it, and there was iron from rust. And due to static electricity, they provided the activation energy, actually caused the thermite reaction to take place, which caused the Zeppelin then to explode. So there's an episode of Mythbusters on this as well.
How did they never really figure it out? I thought, like, how I do it.
It was a thermite reaction.
It wasn't like static charge or anything.
Well, the static charge,
Started.
it provided the activation energy for the thermite reaction,
Yeah.
which then caught the hydrogen on fire.
The thermite, what? Where was it on the Hindenburg?
It was in the paint
Paint.
and also then rusted iron.
And that's on the blimp.
Yeah,
Yes.
the Zeppelin.
Is that
Yes.
lead?
No, it's not a lead Zeppelin. This is an iron Zeppelin. There was no stairway to heaven. Well, maybe people got there fast.
Funny.
So, like, when you're structuring the test, are you gonna give us values of that?
Usually, I'm trying to think. I can't. Yeah, because usually it's always there. I mean, it's open books. You can look it up. But usually, yeah, I just give you the answers. That sometimes the elements are not listed as 0 specifically. So sometimes because the questions are randomized. So if there is an element, frequently Pearson does not give you the heat of formation of the elements.
So can we just Google that?
You can Google it, yeah. I mean, I'm surprised you didn't think about doing that before, but
No,
it's fine.
No, but like what if the values are different? Like, so,
You mean in Google versus?
yeah. I agree with that.
You can get different number of sig figs, and you can get different units. So that is I mean, I do that with my periodic table. I have the periodic table app. It gives different numbers than the textbook.
Yeah.
But it's actually the periodic table app has more numbers, and it's more of a sig fig argument. So
How does the test treat it?
Because the FE203 that you have, it's different.
it is
Well, it's by 2, but
by 2, 824.2. Let me.
we can fix.
Yeah, if it's different, how does the test look through it? Like, how does the test treat it?
How does it? Wait, I'm sorry. Say that one more time, please.
How would the test treat, when like the answer is slightly off, just because of the different
The
standards?
tolerances, there's a little bit of tolerance. I don't remember exactly how much. Okay, let me look it up for iron. Okay. And it's alphabetical. Here we go. Fe2O3. I'm looking in the back of the book. This one lists as 824.2 kilojoules per mole. Did you find it to be negative 742.2?
No, it's -826.
Okay. I mean, you just Googled it right now?
Yeah.
Okay. I mean, that's close-ish. I don't know if it's going to be the tolerance. I mean, if it is an issue like that, just, tell me after the fact.
Okay.
Yeah. No, one thing, so if you study teaching theory, I mean, like the taking people's cell phones away and or the internet equates to what they refer to as a mental amputation. So, I mean, like, you know how panicky you feel when you can't find your cell phone? I mean, like, I got so much stuff in there. I mean, we are at the stage of our human development that we're actually getting dumber. Our brains are getting smaller because we're storing information outside of our brains.
Oh, the phones,
What's that?
because of the phones and the internet?
Yeah.
Yeah.
Or even just writing things down.
I know we don't write anymore.
Yeah.
It's hard to spell things.
Yeah.
No, I feel that.
Yeah. So, I mean, and also, what's the value of education? What is the point of education? And I mean, there are very few instances that you're not going to have access to these resources, right? I mean, if you are, maybe if you're a brain surgeon and you're doing surgery, you can't look at your cell phone then, or something like if you're,
Where does the left artery?
I mean, but I mean, if you're the kind of work that a chemist is doing, if you're doing calculations, yeah, you're gonna have the internet, you're gonna have your textbooks all in front of you, So that's my thought.
Like in the real world.
Yeah.
Yeah. Well, I know it's weird when you go to school and you can't look things up in the real world at your job and just do it.
Yeah, and calculators, and who's gonna do?
Chemistry, like, you kind of rely on just these data tables and.
Yeah.
Right, like that's it's meant to Google or be Google, right?
I think you heard the stereotype where the nerds always had like a bunch of books with them. I think it's from the data tables. Because like people in sciences used to have to carry data tables with them and or logarithm and trig function data.
Oh, you.
I mean,
if you were to take this class in the 90s, you would need like tons of textbooks,
yeah,
access to tons of textbooks.
I took this class in the 90s.
And
we would have to fight over who had access to those textbooks because they're huge.
yeah.
Like when we're doing our homework, we'd be like you have Perry's handbook, let's look to see where that value is. Nowadays it's just a Google, done.
Yeah. So it was part of that to do like what we do.
Well, it's probably more rewarding. You probably want to learn more.
I don't know. I mean, asking what's harder. I mean, then again, like when I did homework, I'd have to type it into a computer and have an argument, with the computer.
Yeah.
So actually, I think I had it easier.
And your teacher, obviously, if he saw like your credit, your work, he would give you credit. Yeah.
I mean, as far as like how we will do as like professionals, I think that it's about the same as preparing us for the future. Do you think like those people were more prepared?
I mean, one of the differences, I mean, I had this when I was a student as well. Things just change so fast. You just have to learn how to adapt. I mean, and that's part of it. And I mean, we've all had to adapt to this whole Zoom stuff and thing. I mean, I was actually I had a discussion yesterday about this, like, what are we doing? You know, how are we preparing our students for the future? So my shut up alarm's going off in 1 minute. So I'll spare you that's the answer there. It's gonna be aluminum, or it's gonna be sapphire. Al2O3 minus rust. So it's going to be the minus 1675.7 minus a minus 824.2, and that gives you A. So any questions with that? All right, sorry to keep you 30 seconds after. Class is over.